In this lecture, we'll be reviewing a little bit of linear algebra as it pertains to this course, and as well as an introduction to Mathcad to show how we can do some of these things a whole lot quicker using computation and power of the computer. A couple of things I want to state up front that I'm assuming you've already had a course in linear algebra, so I'm not going to hit on things in depth, but just the things that are important for this course, just being a refresher. I will be using Mathcad Express for this particular lecture. In the future, it may be a form of Mathcad Prime that needs a license, but at least for this one, Mathcad Express, which is free from PTC's website, you can download it there and use it along with this lecture. Also, if you look down in the notes for this video, it'll give you a breakdown of different things you can jump to. If you don't want to watch the whole thing, feel free to go down there and jump to different links to what you're interested in. All right, so to get the items that you need for this particular talk, you need to go to the link that's down in the notes, again, to get to the lecture materials. And then we're going to look for folders Notes and a folder Mathcad. If you want to download notes, you can. It's, again, everything you see here in the presentation. And then the Mathcad notes you'll need if you want to follow along in what we're doing there. When you go to the website, you should see this. And for the notes, you can just obviously select this folder, or you can go to the Mathcad folder and, again, download the linear algebra, and this other linear algebra, so the basic calcs and simulation calcs. These other ones may or may not be here depending on where I'm at in the presentation or the preparation of other materials. When you open those files in PTC Mathcad, you should see this. So the first one's basic functions. So you have A through G matrices already made for you. And then for simultaneous equations, you'll see Cramer's rule at the top and then Gauss elimination down below. All right, so if you can set those up, that'll help as you go through it. But again, you can pause and restart as you go. All right, so back to the slideshow here. So first of all, our linear algebra review. Just to highlight what we're doing when we talk about matrices, they have rows and columns. And when we have indices, or usually subscripts that we have with each variable, M is the rows, N is the columns. And when we talk about a particular matrix, we talk about how many rows and columns it has. So if we look at this matrix, it is an M by N matrix. So we call out the rows first, followed by the number of columns. So M by N, this is a, well, we can't really say it's M by N because it's a generic matrix. All right. So each matrix, at least for most of this course, are in capital letters and they're in brackets, and then they're usually boldface. So you can see the example there on the right. Let me turn my pen on here so I can mark this up as we go. All right, and for elements, so within a matrix, you'll see the lowercase letters. So if you go back, let's go back here on the previous slide. You can see all these ones with indices here. So the first indice indicates which row we're in, and the second one indicates which column. So you can see all these have 1 because they're all in column 1, and these all have 2 right here, and here because they're all in row 2. All right, so rows first, columns second. If we go to the column matrices are denoted specifically by curly brackets. By the way, this gap right here, this is just due to the equation editor I was using at the time. So just FYI, you're going to see that in some cases. You can basically just ignore the space. But again, so curly brackets are just for the column matrix. So again, column, that's the second indices, so they're all the same, 1, 1, 1 in this case. If we have a row matrix, we go back to the square brackets. The square brackets are used for both row matrices as well as matrices that have multiple rows and columns. All right, so there's some basic terms for you. Some more terms here, diagonal matrix. Diagonal matrices has elements only along the principal diagonal. All others are 0. So example of this would be here. So you have zeros everywhere except for the main diagonal, which is the blue line there. And you can see that the indices I and J, all right, are both equal. That's where the values are going to show. So again, this is a generic matrix. Those would actually be numbers if it was had numbers there. For the identity or unit matrix, all elements equal 1 on the principal diagonal. So it's a diagonal matrix with 1s with all others 0s. So there's an example of identity matrix. So again, we'll use these often as we go through this course. So basic matrix addition and subtraction. Right, so each matrix must have the same number of rows and columns to be able to add or subtract them. So if we have matrix A with M and N rows and matrix B with M and N rows, we can add those. So here's an example of a 2 by 3 for matrix A. So we got 2 rows right here, and we got 3 columns, 1, 2, 3, and same thing with B. So we can add those, and the way we add those is we add each indice. All right, so we got A11, and we add that to B11, and just stay right there and create another 2 by 3 matrix. So again, you see the A11 here showing up, and here's the B11 showing up next to it. All right, so basic, and then you can subtract again of A minus B. All right, so the basic math overall, you just check out the indices. So whatever C, the indice in the C matrix is just going to be an addition of A, I, and J plus B of point I and J, where I are 1 through M and J is 1 through N. So that's the kind of the generic form. All right, so let's do that. So let's go over to our Mathcad, and let's see what we can add here. So we said it's got to be the same size matrix. So it's got to be either 1 by 3 and a 1 by 3, or a 2 by 2 and a 2 by 2. So as we look around here, we can see the only two that are the same dimensions are A and D. So if we come down here, just click at some spot down here in the open, and we just can type A, because A has already been defined as that matrix up above, plus D. And all we have to do now is just hit equals, and it shows the addition. So we can do a real quick check. This is pretty easy. So 2 plus 4 gives us 6, right there. 3 plus 3 gives us 6 again. All right, so it looks like it's doing just fine there. So that was the only two it looks like, right? As we look through here, what we have right now is all we can do. So again, really straightforward there with Mathcad. Let's go do subtraction real quick. Let's go to that. So we'll come back and we'll do A. So I just backspace there, and I got A minus D. And I hit equals there. All right, and again, we see 2 minus 4 gives us the -2, and 3 minus 3 gives us the 0. All right, so let's go back to our presentation here. All right, so matrix multiplication, if we multiply by a scalar, we just make the scalar times each element in the matrix. All right, so if we want to take some scalar B, and we want to multiply it times our matrix A, we just take B and multiply it through by each term. So we got A, B times A11, and B times A12, etc., etc. Okay. So let's do that. Again, pretty straightforward. So we can do this with any matrix here. Let's get rid of that. Minimize there. All right, so with scalar multiplication, we can do it with anything here. So let's we haven't done B yet, so let's go B. So let's do 6. 6 is our scalar. Get my cursor out of the way. 6 times B, and again, just hit equals. And let's check it here. We got 3 times 6 is 18. Looks good. 2 times 6 is 12, etc. All right, so that looks good. And just for fun, let's do another one. So we'll do 2 times, and we'll do letter C there. All right. So to get the dot there, I'm just telling Shift 8 to get that multiplication sign. That's what I'm using there. All right, so 2 times 1 is 2, 2 times 2 is 4, and 2 times 3 is 6. So 2, 4, 6 looks good. All right, so that looks good, just multiplying by a scalar. Now, if we want to multiply two matrices together, so if we got A and B, then A is what we call the pre-multiplier, and B is the post-multiplier. So it's just in order. And order matters here. We'll see on the next slide. So what we're saying is the number of columns in the pre-multiplier must equal the number of rows in the post-multiplier. So the number of columns in the pre must equal the rows in the post. All right, so here's a nice case of it. So we got generically, we got M times N, M rows and N columns. In rows of B must be equal to the N columns of A. Because then once we multiply them, MP, so M rows times P columns, that's what we have for C overall. All right, so that's why they have to match up. We'll see as we multiply. So here we got A is a, we're going to count rows first. So you see 1, 2, 3, 4, 5. It's 5 by 1, 2, 3. So 5 by 3 columns. And we got 1, 2, 3 rows. All right, looks good. So we should be able to multiply those. So those 3 match. And we can get C. And C is going to be a 5 by 4 matrix. We multiply A and B together. All right, so the generic form of all those elements in C, we can find out what C are by summing, looking at K equal to 1. So looking at all the columns in from matrix A and all the rows from matrix B and changing those from 1 to N, summing them up, and we get what this C are. All right, so let's do that. Okay, get this keep popping up on me there. Sorry about that. All right, so we need to find the one that has the columns match the rows. So columns match the rows. So if we look at A here, we got columns is 1, 2, and that matches the 1, 2 rows of B. So that should work, and it should come out to be the rows of the pre-multiplier times the columns, or by the columns of the post-multiplier. So this should come out to be a 3 by 3. So let's take A times B equals, right, so it came out and worked. Right, so let's go back here and actually just see, what if we do just A, B, and equals? No, it doesn't like that. So that's sees that as a variable. So you got to make sure you get the times multiplication symbol there. All right, so what happens if we don't get them right? So A times D should not work. So let's do A times D and see what happens here. All right, so these array dimensions do not match. So Mathcad will give you a little bit of instruction. Hopefully you can pick up from that what was going on there. So you got the columns don't match the rows, and that won't work out. All right. Another one that would work here, let's look at also B times C. That should work. So we got 3 columns for B, and we got 3 rows for C. We should end up with a 2 by 3, right? So B times C equals, all right, good. So I got 2 times 2 by 3 matrix there. All right, so again, pretty straightforward for multiplication there of those 2 matrices. All right, so overall here, if we got more than one matrix, cumulative, no, it's not a cumulative. So A times B does not equal B times A. Or not necessarily, let's put it this way, not necessarily equal, no, scratch that. Let's just say it doesn't equal that. We'll see that in a little bit. Associative, so we got A times the quantity of B times C is equal to the quantity of A times B times C. And you can see that the order of ABC is equal to ABC. So you got to maintain that order for the associative part to work. For distributed, again, that works if you keep everything in order. So we've got A plus B times C equals A times C plus B times C. All right, and you got to keep those in order. So A, then C, B, then C. You can't go, I'm not sure what else you would do, but try to do C times A or C times B. It's got to be A, C, and B, C. Same here, A, B, and then A, C. All right. So again, for square matrices, we could multiply those. We could put like some superscript up here, do an exponential, and say, hey, A to the 5. So you could just make up a bunch of A 5 times in a row, and that would work. We also multiplied by the identity matrix on either side. So the cumulative rule is actually true for the identity rule, but not for some other, with the identity matrix, but not with some other matrices. All right, but it ends up being just equal to the matrix that you're multiplying the identity matrix by. All right, so partitioning matrix. So this is another way we can multiply matrices. So we get these larger matrices, and they become valuable when you get really big, requiring less computer memory. What we can do is we can take this as a 5 by 6, and we can split it up. All right? Somewhat arbitrarily, but depending on what you're doing, it'll be kind of dictate what you're doing. But we're going to split this up, and so what we see here with this A11 and this A12, A21, A22, that indicates which one of these sectors. So A1 and A11 is this area right here, and we can see these down here. So that's that section there from A12, that's the upper part over here. A21 is the one down here, and then A22 is the one right here. All right, so it's all broken up like that. All right, so we'll use that as we look here going forward. All right, so partition matrices, how do we add and subtract them? Well, we need B on another 5 by 6. And it has to be partitioned the same as A, then we can just add them straight across. We can add up these little mini matrices we made, the minor or sub matrices we made from one, and add it by the other one. All right, and all right. So for multiplication can be formed only when the number of columns in the pre-multiplier matrix is equal to the number of rows in the post-multiplier matrix. All right, so same thing as before. So we need to make sure we partition these up. So we already have the A matrix, and we had it partitioned. And now we can partition the C matrix, a new matrix, up. And this one was overall is a 6 by 3. So again, the overall number of rows, 1, 2, 3, 4, 5, 6, equals the number of columns of 1, 2, 3, 4, 5, 6. All right. So let's see what happens here. This one breaks down. We got, again, C11 is this part up here. C12 is this one. C21, and then C22 is right here. All right, so those all match up to get with A. Let's go back actually one slide to see that. So this one, we got 3 columns, so that'll match up to 3 rows. we got 3 columns, 3 rows, 3 columns, 3 rows, 3 columns, 3 rows. So those can all be multiplied by each other. All right. And the way we do that is we take, again, just A times C, and we have all the ones broken up, but we got A111, and it can be multiplied by AC11 there. And we go forward from there. So we got A111 times C111 plus A112 times C21. So again, we're taking the row multiplied by the column, and that gives us the first point up here. And then we have the next row, or sorry, the same row multiplied by the next column gives us this second indice here, etc. going on there. All right, and so we get D is our new different areas, and those are the multiplications there. All right, so pretty straightforward, but again, a lot of this is beautiful because computation can take care of it for us. All right, next section here, let's look at transposing matrices. So finite element formulations, we're going to be doing this a ton. Frequently can be solved more efficiently through transposing matrices. So we'll look at what that means here in a little bit. Transposing matrix creates a new matrix with columns created from rows of the original matrix. All right, so let's look at that here. So here we talked about this, or we'll talk about this a lot, the element stiffness matrix. So it's a 2 by 2 here. And this is for the first element, and we want to get it to a particular form of the global stiffness matrix. So this is one element in a larger piece that we're looking at. So we need to get it into this bigger matrix that will include all the different pieces. But this was just for the one. So how do we get from this 2 by 2 into this 5 by 5? And so that's what we're going to work on here next. Excuse me. All right, so here's how we're going to do this. We're going to have these two matrices. So we got A1 and A1 transpose. And you can see we got only just some ones in the first row, first column, and the second row, second column. All right, so if we multiply this transpose matrix, so this one here, if we multiply this times our 2 by 2 stiffness matrix, and then we multiply that by the first matrix we have, what we come up with is our global form of the equation. So again, here's the first one, here's the transpose, here's the stiffness matrix. So this is a 5 by 2, and multiplied into a 2 by 2. So we get another 5 by 2. And then we're going to take that 5 by 2, we're going to multiply it by a 2 by 5, and getting this overall 5 by 5. And because of where these ones are, we'll see that that helps to place where those k's are. All right, so let's do that. So going back to our Mathcad here, and we're going to scroll down. Well, we did this first here. So again, we saw that we have the transpose there. So we have F, I've already defined this, is the transpose of E of E. So the transpose of E. So here's E, and so we want the transpose of that. So just hitting equals on F, because F has already been defined here. Hitting the equal sign shows me what it is. And we get that to occur there. So now it says we need the transpose. So F is the transpose of E. So we'll put F first. F times, and what are we going to transpose? Well, it has to be something that matches the number of, I think I got these mixed up. Oh, yep, so you want the vertical matrix there, more vertical matrix first. So we want E first. So let me put E there. Backspace that out. So we got E. So we're going to do 3 columns into 3 rows. So it could be this one, could be this one, could be this one. We actually want to do this guy right. It's going to be a square matrix. We'll multiply it into a square matrix. So we're going to do C. So E times C times the F we create over here from the transpose of E. All right, so we can rewrite that. Actually, let's put that in. So we'll put E, and then the transpose of E. And I'm going to explain about that in a little bit. How I got the T there. All right, I go ahead and hit equals. All right, and you can see we got that C 1, 2, 3, 2, 5, 3, 1, 0, 8. 1, 2, 3, 2, 5, 3, 1, 0, 8 up there in the upper left-hand corner. Right, so that's now the 5 by 5 matrix. So that's what we want there. All right, so let's talk about a little bit more about what we did there. So Mathcad notes, something we just did here. When you do the transform of a matrix, do not use a superscript or shift 6 on most keyboards. T. That will not get you the transpose. That will get you something you don't want. You need to use the way how I got it is you use Control Shift T. That's the shortcut. Or select from the ribbon. So if you forget, you can go to the ribbon. So let's go back down here and do this again. Let's do this for a letter we haven't done yet. I'll do R. And I'm going to do R. And when you do colon, that's the definition. So you see up here, there's a colon equals. So how I got this colon equals is I did R and then typed a colon. So Shift the semicolon colon button there. All right, so that gets, I'm going to define R as E. Oops, I clicked the wrong spot there. E. And so here I'll show you the difference here. So I do superscript T. All right, we'll see what that does. Right, these units are not compatible, so we don't want that. So delete that out or backspace that out. So Control Shift T, and I get equals. So actually, notice the difference. See how this is not italicized, and if I do the caret, so Shift 6, so try to do superscript T. See how the T is italicized? So that's what you don't want. You want to see an unitalicized T. The other place you can go is go over to, actually I was right there, to the matrix operators, and you can go here, matrix transpose. And you can see there it says Control Shift T for the shortcut there. So click on that, and you get the T there as well, and you get it equals. All right, so two options there. You can go up again, matrix operator on the matrix tables ribbon, or Control Shift T. All right, the other note I want to highlight, Mathcad should update automatically as it's doing the calculations, but if it doesn't, you can use Control F5, or again go to the calculation tab and select calc. So just let me show you how that. If I hit Control F5 right now, you can kind of see everything goes gray and then comes back. All right, so that's showing it's recalculating. You can also go to the calculation tab here at the top, and right here and click calculate. But again, you see this how this is already selected, so it's auto calculating. As soon as you do a calculation, it should update everything. But if you feel like it's not, then Control F5 or come to the ribbon here and do that. All right. So transpose example number 2. So we put in one element into our global matrix. Now let's put in a different element that's in a different spot. So we still got the same structure here. And we're going to have this transpose matrix here and the other side matrix on the other side. So here's what A2 looks like. Notice how we move the ones here, right? Because we're dealing with a second element, and so it's not going to be in the same position as the first element. So we got A2 and A2, the transpose of A2. And there you can see as we get our stiffness matrix in there, it comes in this spot right here in the middle, right, as opposed to the upper part. And then what we can do is we can ultimately add all these, so we'll have 1G plus 2G plus 3G, etc. All right. And I will talk more as we move forward about how we structure that. All right, so transpose summary, again, in general, to obtain the transpose of a matrix, X, or in our case we used A, size M times N, the first row becomes this first column of the transpose matrix. The second row becomes the second column, third row becomes the third column, and so on. So XT will be the size N by M. All right, and so there's some transpose operations you can do. So if you take the whole quantity and you want to transpose that, it's the same as taking the transpose of each matrix by itself. And again, if you do the multiplication of a bunch of matrices together and then take the transpose of that, it's the same as taking the transpose and reversing the order, taking the transpose of the first one, taking the transpose of this one first, and then working your way backward, because see how X is here, and now A is the last term over here. All right. So again, just to show you that transpose action. So we have the first row here becomes the first column here, and the second row here becomes the second column here in the transpose matrix. That's what that was talking about. All right. Symmetric matrices. All right, so symmetric matrix can only occur if you have a square matrix. The elements are going to be just swapped where you got A at position M in is going to be equal to the A element at position N M. And therefore A is equal to the transpose of A. So here's an example that will hopefully clear things up. All right, so if we look at 2, 5, 9, 10, 5 down the principal diagonal, you can see those are all different. But if we look across the diagonal, we got 3 and 3 are the same. We got 6 and 6 are the same. We got 10 and 10 are the same. So that's what when it talks about symmetric, what we're looking at there. Determinants. All right, so the determinant of a matrix is used for solving a set of simultaneous equations. It's also used to determine the inverse of a matrix, as well as forming the characteristic equations for a dynamic problem or an eigenvalue problem. So we're going to look at this for a couple of these cases. It's only defined for a square matrix, as we'll see here, and the determinant will result in a single number, so it will result in a scalar number. So a couple ways this can be denoted. We got capital D determinant, or lowercase d determinant, and then here we just have straight bars around some matrix letter, or straight bars around the actual elements. All right, all those 4 different ways really to show that we want to take the determinant of this matrix. All right, so the definition is for this particular matrix, right? The determinant is, again, straight bars around A and then straight bars around the elements there equals these values here. All right, so A11, A22, A23, so right down the diagonal, A12, A23, A31, etc., etc. So we'll talk about where this comes from and different ways we can calculate this, but that's the definition. All right, so solution procedure. Here's option 1. This is called minor lower elements method. And what you can see we're doing here is we're taking A11 up here in the corner and then multiplying it by A22, A32, A23, A33. So basically multiplying times this section down here. And then we got A112, and we're taking the subtraction of that, and we're subtracting off A21, A31, and A23, A33 shows up right here. And then similar for the last term there. All right. Where the determinant for A22, A23, this term right here, we can break that down and we say A22, A33. So that's these two terms multiplied together minus these two terms multiplied together. Right. And similar with the next one as well as the next one. So you might be seeing a trend there, and we'll see that as we go forward here. That's something's going on there that's important. All right, so option number 2 is we can do a direct expansion method. All right, so if we can see here, we got B11, B22, the matrix for a 2 by 2, or the determinant for a 2 by 2. We got B11, B22 shows up here, minus the going the other direction. What we have there is we add solid arrows going down to the right, and we subtract dashed arrows down to the left. All right, so on a 3 by 3 matrix, we're going to add those, but you can see we're going to run out of variables because we're going to go 12, 22, 33, 12, 30, 23, there's nothing here. All right, so basically put the whole matrix out right here, and then add on the first 2 rows, 1, 2, 3, and 1, 2, 3, put those right here next to it. So now what we'll do is we're going to add, so we include those columns here, we're going to add everything down and to the right, starting with the first value here, and then we're going to add all those together. So down to the right is the first value there, right, 11, 12, 22, 30, sorry, 11, 22, 33, plus 12, 23, 31, plus 13, 21, 32. And we're going to subtract, go in the other direction. All right, so we got subtraction of those terms. Right, and that gives us a determinant for a 3 by 3 matrix. Now we can't use this for any higher order determinant, so that only works up to a 3 by 3 matrix. All right, so it's kind of limited in that regard, but we can still use it in that process. So here's examples of option 1. So method 1 is more versatile. So what we can do is we can break down. So again, 4 by 4 matrix. So this is what we can do here. What we do is we're going to write out this matrix 4 different times, or at least practically we won't do this, but kind of just to flesh things out, see what's going on. We're going to take that top term, top left term, and we're going to ignore the rest of the stuff in its same column and same row. You just basically cross them out if you need to. We're just going to look at that top C11. All right, we're going to take what's left, actually in a sec. So next one is again C12. I'm going to cross out and ignore the rest. C13, ignore the rest. C14, ignore the rest. All right. So now we're going to take that term there in the upper left-hand corner, the blue box term, and it's going to show up here as the one gets the multiplier, the scalar, the multiplicator, after we take the determinant of what's left. So here's C22, C22, C44, C22, C44. We do the same thing for C12. We're going to ignore this row. So we got C21 through C41, 21 through 41, C23 through C43, right, and then ignore the rest. Right? So same thing the rest go, and you see how we switch from minus to plus to minus as we go across. So the first one's positive, negative, positive, negative as we go. All right, so minor of minors, if we have now our 3 by 3 matrix, so that's this one right here. All right, so we're going to take that matrix, right? And again, we take the one in the top left-hand corner, we ignore the rest, and now the C22 shows up here, and all the rest shows up at the other spot right here. All right, and we minus and then plus. All right. So again, it's a great way to do it by hand, but hey, we can use Mathcad and things go a lot faster. All right, so let's go back here. And I think we actually already did multiplication, but we can do it again here. So we got, oh, sorry, we didn't do determinant yet. So again, we have to do this on a square matrix, and it looks like all we got is C here. So just take the DET, and I'll put parenthesis, and I get both parentheses. So I just put the left parenthesis, and I get both of them show up. Type in C, and then just hit equals. I don't have to move it to the end. Just hit equals, and I get -1. I'm going to do this a different way. I'll just hit enter. And this time I'm going to hold down shift, and there's the, I believe it's called the backslash, but it's usually right above the enter key. Hold down shift, and if I hold down that and click that, it's the vertical bar. It's almost like 2 vertical dashes on your key. But you can see when I do that, it gives me that 2 vertical lines like I'm going around a matrix. And I can again call that on C and hit equals, and I can get -1. So 2 different ways there we can call it the determinant of matrix C. And let's, to be crazy, let's see what happens if we do something that it should work on. So again, I'll do the shift bar, and I'll do it on B, and hit equals, and see this matrix must be a square. Oh, it gives you Greek. So the same number of rows and columns. All right, so we know that what happens when it doesn't work. All right, so let's go back here. All right, so review what we've done so far. We looked at methods to manipulate matrices. So we did some addition, subtraction, multiplication. And we also showed methods of partitioning, transposing, and finding the determinant. All right, so that was our little bit of linear algebra review with some Mathcad application. Now what I want to look at is solving linear equations. So specifically 2 different methods, Cramer's rule and Gauss elimination. All right, so let's look at that as we go forward here. So Cramer's rule says that if we have some linear algebraic equations, right, so we got our variable, what we're trying to solve for here is x1, x2, and x3. So we got 3 equations with 3 unknowns, x1, x2, and x3. Put those in matrix form. Right, so we're going to have all our A's components up front here. Here are the variables we're trying to solve for, and then here's some solution value B. What Cramer's rule says, so remember A and remember B. Right, so A is our square matrix, B is our vertical matrix. What Cramer's rule says is we can find what x1 is by taking the total A matrix and the determinant of it in the denominator, and in the numerator we replace the first column with the B values. For A2, right, same denominator, but in the numerator we now replace the center column with our B values. And for x3, we're replacing the last column with the B matrices. Right? So stuff like that. Or another way we could write this is we're going to put column B and column 1 of our determinant of A. Put our B column matrix in column 2, of our determinant A. And we'll put our column matrix B in column 3 of determinant A. Right, so a couple different ways we can kind of explain that, but that's what the step looks like. So let's go do this. All right, so this is your other file, your simultaneous equation file. So again, Cramer's rule. So here's our original matrix, and here's our solution matrix. So this is the B matrix, this is the A matrix. And so what I've already done, I swapped out column 1, column 2, and column 3. So you can see 5, 4, 6 is in column 1, 5, 4, 6 is in column 2, 5, 4, 6 is in column 3. And now I have the determinant of the original matrix, or our A matrix, the determinant of our swapped out matrix, and those are all those cases. So this should be x1 should be equal to minus negative a2. I'm just clicking on the equation and hitting equals. X2 is 27 and x3 is 11. So these are all a result of if we had original equations of 1 times x1 plus 2 times x2 plus 3 times x3, all that equals 5. These are the results of that along with the subsequent equations below. Now I don't have anything else to compare this to, but I do have another method up which I'll show down below, and we can compare the results. All right, so let's go back here. All right, so Gauss elimination method. So we got linear algebraic equations, and we have this particular case we've got 2x2, no component for x1, basically 0 for x1 and 0 for x2, all equals 0, etc., etc. You can see there. So we're going to put these in matrix form. So we got matrix A and matrix B, and our values we're trying to find here. And so this is kind of a key method by hand. You can obviously do the other one, Cramer's rule as well. But this one, it can be faster depending on things what are like. All right, so here we got A and B combined. So what we basically did is I can go back. A matrix is a 4 by 4. Right here, we're going to take B matrix and tack it on the end, so we end up with a 4 by 5. So we got a 4 by 5. So here's the original A matrix, and then here's our B matrix. So now 4 by 5 matrix. And what we're going to do here is we're going to swap row 1 with the row containing the largest value in column 1. So the row 1, we're going to swap out this one with 6 because 6 has the biggest value in column 1. So we see 6 now is 6. The whole row for 6 is now at the top, and the whole row that had 0 in it is now swapped from where the 6 was at. So now what we're going to do here is we're going to make all elements in the first column except row 1 equal to 0. And in row 1, we want that first term to be 1. So that's what we're going to do here. We're going to start dividing row 1 by 6. So this was a 6 right here, and we're divide that by 6. So that's where we end up with 1/6 here, -1, -5 or 6 and 1. So this is what we want. We want that 1 there. Now we want these all to be 0. So we're going to 0 here, so that's good. I'm going to get rid of those two. To do that, we're going to multiply row 1 by the column 1 term in row 2. So that was 2. And then we're going to subtract it from row 2. So we're going to multiply 1 by 2, and 1/6 by 2, and -1 by 2, etc. And then we're going to subtract each of those values from the value right below it. So now we got 2 minus 2, 2 minus 2/6, 3 minus -2, 2 minus -10/6, minus 2, -2 minus 2. All right, so the results of that. But then we're going to also multiply row 1 now by column 1 in term in row 3, which is 4. So again, we're multiplying this first row by 4, and then subtracting from this row, and those are results there. And we'd also do this, we multiply row 1 by the column 1 term in row 4, but it's 0 in this case, so there really is nothing to do in that regard. All right, so what we have now is a 1 and a bunch of zeros. And now what we're going to do is we're now trying to change this value to 1, and then the rest of its column to 0. So that's what we're saying here. So we're going to swap row 2 with the row containing the largest value in column 2 except row 1. So that was this 22/6, that was in row 3. And now we're going to start to make all those elements, as I was saying before, the same as what we did in column 1. So we want -22/6 to be 1, and then we want to take out the other 2. All right, so we divide through all of row 1 by -22/6, so we get the 1 right here, and now we're going to take out the rest here. So multiply by 5/3, and then subtract that from row 3, and then multiply by 2, multiply row 2 by 2, and then subtract that, and we get the results there. So now we have our 2 zeros, we have our 1, and the 2 zeros. All right. Now in column 3, we want the same process. All right, so we're going to first divide column 3 by 225/33 to get a 1 there, and now we're going to take that, multiply that by 24/11, so subtract it from the 4th row, get those results so we can get a 0 right here. All right, so resolution there, we got a 0. All right, and now we still want to get a 1 here in this last spot. All right, so we're going to divide through by 3,861 2,475 to get our 1 right there. All right, so that gets us in a good spot here. Why? Let's see here. So we return the original matrix form. So now we have just the first 4 columns here, and then the last column was again our B column. But hey, look what happened. If we would put this back in equation form, we would have x4 equals, because it's just a 1 here, x4 equals negative 7,722nd, 3,861st. There's our value for x4. So x4 is equal to -2. Right? And we can back solve then using x4. Since we know x4 from this row, we can now solve, we know what x4 is up here, so we can solve for x3, etc., etc. And so we can solve for all those values and find what x1, 2, and 3 are at. All right. So let's do that. Now we're actually not going to do Gaussian elimination per se, but we're going to do the Mathcad for that. So we're going to actually just take the inverse of matrix A. So here's our 4 by 4 matrix, and here's our basically our solution, or our B matrix, or A matrix, B matrix. And if we take the inverse of matrix A, multiply that times B, we can basically solve it for x, y, and z. So this is the same one we just did, right? The example we just did, and you can see that it's negative 1/2, 1.333, and negative 2. Oops, what do we go here? So negative 1/2, 1.333, and negative 2. And going back over here to our original previous problem, we did Cramer's rule. We just hit equals on that. So we get negative A2, 27, 11, and we get negative A2, 27, and 11. So again, this is probably the quickest way. Just type in the two matrices and then take the inverse of your square matrix here times B, and you get the results. But again, just two methods if you end up needing to use them: Cramer's rule and Gauss elimination. There's also MATLAB ways to do this. Obviously, MATLAB Matrix, and so that's a big thing in what they do in that program. I'm not going to go into it here. If you want to check it out in the notes, it is there, but I think it's probably all over the internet of how to solve those things. The focus of this class is going to be using Mathcad, but again, you're welcome to use MATLAB throughout as well. All right, hope you enjoyed that, and can be able to view other lectures as they come.